So last time, which was last night, so it should be very fresh in your memory unless you just completely erased it. I have basically gone through explaining of how am I flowing around the sphere. Okay? And in porous media today I brought some visuals. We can often think about the sphere. I either have a fluid that is carrying particulates. Okay? So I have either drilling mud or pieces of sand that are carried with that water. So that's something that I might want to look into. Or I'm looking at the settling in my fluid or whatever it is that it might be carrying. Or in essence, if I have a granular medium, this is a very beat up a 3D print of a sphere packing. Sphere packing is common both in the labs, but it's a common model for unconsolidated sand or soil. You are essentially flowing around spheres. Now it's a very constrained flow. It's very far from the example that we showed where, oh, I have this one sphere and then everything empty around it. So it's very far-fetched from that. Okay? But regardless, actually, there's this entire upscaling scheme called unit cell approach that uses that approach and still figures out how to go from Stokes formula to permeability formulation for sphere pack. We are skipping that part because they're skipping streamlined solutions. But nevertheless, there's, again, flow around submerged objects is a very common porous media. So if you want to just amuse yourself with these spheres, you can. And I have some other examples for later. And then this would be a sand pack. So this is a piece of a sand pack. Okay. So just to wake you up a little more this morning, let me try. I'm just going to give it a shot to change this PowerPoint. No. I managed to actually in Bronze Room figure out how to change this slideshow to show correctly up there. And now that same, so show. Will this help? Hey! All right. It works here too. I figured it out in Bronze Room, but then it doesn't always work, so it's a strange thing. Anyway, it works now. I'm not gonna touch it. So, maybe it works. Now I can't move. You must be kidding me. Never mind. So this was set up. I'm just gonna continue. All right, we're gonna play with this more later. Somehow I managed to click some options, and it actually worked and changed. And I thought that I recalled what I'm supposed to click, but apparently not. It's shown correctly on my screen. For what it's worth, I just can't flip them. All right. So basically what we said quickly, if I have, just a brief review, if I have sphere in sort of infinite amount of fluid, and I have that fluid is flowing in one direction, which I denote as Z, then basically because of the curvature of the sphere, to get around that object, there's essentially no way to have only one non-zero velocity. I have to have two non-zero velocities. Essentially because sphere is curved in two orthogonal directions in 3 dimensions. Okay? And I cannot get around that. Cylinder is curved only in one direction, in the other one it's straight. So I can get around that. So I can get the symmetry and things being the same the way I slice them. However, I can't do that for sphere. It's kind of, I can slice it one way and it's curving, and then I slice it in any orthogonal direction, it's going to be curving again. Okay? So because of that, I need two non-zero velocities to actually get around it. So if we introduce spherical coordinate system, I think about, so I can slice it in phi direction. In phi direction, basically, however I slice it for any phi, right, around the sphere, I'm good. I see the same thing for the flow that is well developed. Okay? But I cannot get away with doing the same in theta, so I do have dependence on both r and theta. Okay? And I can see that here in the streamlines, essentially. I have dependence on these streamlines both in how far away I am from the sphere center, as well as where I am. Am I here, 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 here? Right? So that's that dependence both on theta and r. Now, when I can apply boundary conditions or think about what boundary conditions to do. So basically, if I look at my spherical coordinates or my equation of motion for spherical coordinates, it looks ugly. Okay? It's no different from what we actually looked at already. This is rho times dv dt, r component of it, okay, and material derivative. So this is my basically acceleration in the moving, okay, moving window, moving with the fluid. And then I have the r component of gradient of p. Okay. Then I have this here is Laplacian of v, r component of it, okay, which is essentially Laplacian of vr. Okay. And then the r component of the external velocity. So this is still my same, my equation of motion that I'm used to. It's just once I write down what all of the things are in spherical coordinate system, it's pretty complicated. And the same for v theta and v phi. So if I were to simplify this, okay, my v phi goes away, but v theta doesn't, and it does depend both on r and theta. So in this case, both of these terms stay here. Okay. So essentially, and then some of them will go away, and I'll even get like VR v theta here. Okay. So this does not simplify to anything that I can actually solve analytically in the form it's given. Stokes did come up with a way, because it's not just VR v theta, it's also pressure. So those three things are coupled in a complex way in these equations. So he found a way to basically get away with or remove pressure from the equation. And that's if I go to the original equation of motion, I will see gradient of P there. If I take curl of that equation, curl of a gradient is actually zero. Okay? When I have a potential field, its curl is always zero. So potential field means that it's a field, vector field, where I can find a function such that that field is gradient of that function. Okay? Electricity field, electric fields are like that. Okay? So in any event, I can remove that pressure from that equation, but then I'm getting a higher order equation in velocity. Okay? So that's again not so easy. So the procedure would take us a moment. It's called streamline solutions, and those are elaborated in chapter 4.2 in BSL. Should you ever feel bored, okay? Videos are available from the previous years on my YouTube. This should kill your boredom right there. Or put you to sleep, one of the two. So there's actually a story related. So this vorticity equation, when you take the curl of the equation of motion, can take a moment to start writing down. And then, so it's like an hour or so exercise in itself. And then there was a streamline solution after that. So a couple of years back, I believe it's 2011, but now I don't remember correctly, 2010 or 2011, there was a shooting on campus. And they locked us, we were at that point in CP 204, and they locked us in that room while they removed the shooter on campus. So basically somebody just came in and locked us from the outside to stay safe inside. And we went on and on for 2 hours. It's funny now, but I was like, what are we going to do? Are we going to now sit and ponder the situation on campus? No, that's not a good idea. Like, that just creates panic. Let's just calm down and derive work. So anyway, I still laugh about it. And I didn't even think about it twice. It's a correct decision to make in a high-stress situation. Just keep deriving, whatever it is, don't think about it, because you're thinking about it and stressing about it won't help. So just wait for them to come and unlock and like, but it was the worst possible thing, because it just took forever. But it was a good exercise. Anyway, so once you go through that procedure, which again, it would take us a week and a half or so, you actually arrive at a solution that looks like this. This is my VR of R, and that depends on R and theta. Okay. So we have radius of sphere, capital R in there. We have that V infinity, that's the velocity of the fluid away from the sphere. Okay. And I have theta in this equation. And I have V theta that is in a similar form. One thing that I can just recognize if you kind of go back to if you ever had PDEs, you can see that it's separated. So it's a function of R times a function of theta. Function of R times a function of theta. So basically the separation of variables in this sense helps solve this ultimately. And then my V phi is 0, which is, I assumed before, and pressure is also a function of both R and theta. There's a Z here that's snuck in that is technically not correct to use in spherical coordinate system, but this is a traditional form rho gz. So if I replaced it by R cosine theta, that wouldn't necessarily be immediately seen. There's a pressure at some Z is equal to 0 level that I use as a reference. I always need reference pressure, and then minus rho gz compared to that level. But really, it should say rho g R cosine theta, and this is at theta is equal to 0. Theta is equal to 90. I'm sorry, 90 from the Z. So in that sense, but again, rho gz is so ingrained that it's used this way. So if we actually use this velocity field, I could go and integrate the forces that fluid exerts on the sphere. The way you do that, and that's going to be your next homework, and it's a fun integration exercise, as you might imagine, is you take tau, basically all of the shear stresses on this sphere, and integrate them on the sphere surface. As you do that, you're actually going to get that the overall force acting, so the total of the force acting on the sphere is in the direction of the fluid. So all other directions disappear during that integration exercise. So that is what we typically call drag force on a sphere. And there is inside of that the total forces. It's not just viscous forces. Actually, the pressure forces will show up as well. So there is technically, it's in delta z direction. Okay? So I have the buoyant force that we know from, I guess, high school physics or science or whatever it is, right? But it actually pops out during that integration. And then because I have to, I integrate not just shear stresses, but actually the total stresses on the sphere, and they have the pressure component in there as well. So when I integrate that, I will get the buoyant forces, and then I will get what we call form drag. Okay? And there's basically so there's pressure, which is my standard rho gz, and then there's a flow disturbance part of the pressure field. So if I think about the pressure field, there's a pressure field that was there before having a sphere, and then there's a disturbance from that sort of equilibrium once I place the sphere in there. And when I integrate that difference, I will get this so-called form drag, And then the last piece is actually friction drag, and that's what you get by integrating the shear stress around the sphere. So these three components, and specifically, so buoyant is something that you've probably done in high school already. The famous Stokes formula puts both drags together into 6p mu rv theta. Okay? And that is the famous Stokes formula for viscous forces exerted on the sphere. Okay? Even this is the flow disturbance, so it's taken as viscous flow disturbance because I actually have flow around an object. And I have changes in the velocity field because of that. So together, this formula is used in very slow flow. This is Stokes regime, when my dV dt is actually 0. Okay? So very slow, very small Reynolds numbers. For sphere, they're actually less than 1. For larger than 1, you actually start seeing a little elements of turbulence as you're flowing around this object. Okay? So, regardless of flow often being in non-Stokesian regime and Reynolds number being much higher, this formula is one of the most used formula in gauging what the force would be on any particle in flow in porous media. Porous media or Wellbore. Okay. So, because it's simple and it's easy, so it's some sort of like a baseline. So even if it's off, it's still a good first order approximation on the forces around this flow. So formally, it's for Reynolds number less than 1. We're gonna deal with larger Reynolds numbers and friction factors, but whenever you don't know, it's still a good first order estimate to use, and it's very simple to compute, so therefore it's used. So it's this 6p mu rv theta, okay? And that's the magnitude of the force exerted on the particle by the fluid. The direction is in the general direction of the fluid. Okay? So this is for Reynolds, and so this is for actually Reynolds number less than 0.1 even. Then you can, depending on the Reynolds number, you can actually get this derivation. This is taken from BSL. Again, just put somewhere in the back of your mind, if you get to use this in your research, maybe you're going to deal with top and flow or something of that sort, there are formulas for this force that depend on the Reynolds number. Okay? So for a very small one, all of these terms disappear, but for a larger Reynolds number, you might need a better approximation. All right. So again, it's a very useful formula that is used a lot. There's even measurement of the elementary charge, okay, by balancing all of the forces. A charged particle is a little sphere, okay, and there's definitely drag forces acting on it. Okay? So when you balance that with the electrical field forces, so there was Millikan and Fletcher had this experiment. Basically, they had these droplets of oil, and so when they balanced the drag on them and the electrical force, they were able to find the actual electrical forcing on the particle and find the elementary charge. Okay? So there's, in porous media, much more often, we're going to do soil particle size analysis. Right? So you're going to let the soil settle, and you're actually going to see, depending on the particle size, you're going to see the different time. Okay? So essentially measure the time for separation of different sizes of the particles. Okay? And then you will sort them. So you can figure out the fraction of the sand. So sand will settle on the order of seconds. Silt will take a couple of hours. Clay might be good luck waiting. Okay, because the particles are very small, so at some point that buoyant force is enough to actually keep them suspended. Yeah. So basically then based on that you have, so we refer to stones and cobbles as larger than 64 millimeter, gravel is 2 to 64, sand is 0.05 to 2, silt less than 0.05, and clay is less than essentially 2 micron. Okay. In sand production applications, you actually want to design screens so you have particulate flow from the formation. So if you have weakly consolidated sand, some of this, just like that blue plastic model of mine, a lot of them have chipped off. Okay, now they're chipped off because of people handling them, but technically you could have, because of the flow and friction with other particulates in the fluid, you can have a portion of the formation start chipping off and flowing, and that's not what you want to produce. So often we put sand screens in weakly consolidated formations or unconsolidated even, so that we don't produce sand. So you can amend Navier-Stokes equation in simulators with basically with the movement, it's called discrete element method of individual particles. And for that movement, you need what is fluid doing to the particles. So you calculate the flow field, and then basically also, drag force on each particle in that flow field. And then you let them interact. So that's how you get the movement of the particulate individual particles inside the fluid. And that's important because they can often do what's called bridging. Okay. So even though each of these particles is individually smaller than this opening on the sand screen, okay, they're going to form a bridge and not flow through. Okay. You can probably do that in your own kitchen or whatever. When you're sifting something, you will find that happen. Right? So, or if you use, how do you call it, funnel? If you use the funnel, you will often have, if you have particles, they're going to bridge and not flow down, and you have to shake them vigorously to actually let them down. So that happens all the time. So if you want to design effective screens, then having a simulation method that is again based on Navier-Stokes simulator amended with this individual particles, you need that to design screens. This is work from Somnath Mondal, who graduated a few years back from Dr. Sharma's group. In my own group, we do similar things. So basically, but this is actually flowing through that sphere path. You see the blue one? That's essentially flow through it. So essentially, this is what happens in formation damage. There's a picture out there, but if you have a drilling fluid that is getting into the formation, then it might get basically strained at the sides, and that creates a filter cake. And there's a formation of filter cake here, and you can see the damage inside. Now, this damage inside will impede then the flow of hydrocarbons later when you want to produce from the formation, so it's important to assess. Also, any kind of logging that you do, you're actually assessing a damaged formation, not the original one. So if you're wondering about the reservoir, you're actually assessing near wellbore damage zones, so you have to have a way to gauge how much damage has occurred so you can adjust the measurements you get. So this is just some motivation about that. And we are going to move on to a little bit of visualization. So this is basically in the Stokes formula discussion, so for flow around the sphere and more general submerged objects. We are now going to basically move on to applications of flow or equation of motion inside the porous material. And we're actually going to get to carbon-Hosseini equation today. So there is, or in this week. So there is two approaches. So let me actually get my visual. So any of these porous materials, and I have brought a few, this has passed, everybody has seen some of these, I can send them again. but I'm just going to use some of them. So this is my fractures. These are the fractures that you're often imagining that they're slits. Okay? What I really have is sort of a network of these slits, technically. So this is artificially fractured. This was fractured in the lab. But natural fractures will exist and be complex as well. Now, this is a standard sandstone. Standard sandstone. When I zoom in, basically this is the sizes are typically on the order of microns. When I zoom in, I give or take see pore spaces that are like this. So this is what I'm flowing through. It takes quite a wild imagination to see a cylindrical tube over here. And we know how to solve cylindrical tube. You're going to solve for triangular cross-section tube for this homework. Whatever, you can imagine a relatively simple cross-section. It takes some imagination to find that cross-section in here. Now, in reality, if I can imagine a tube that fits into one of these cross-sections, right? So I kind of inscribe a tube inside of it. That's where most of the flow occurs. Okay. On the side of it, I'm so close to the walls, and I know that I have velocity 0 at the walls, that effective flow in sort of like a very small portion or crevices of the pore space where I'm close to the solid boundaries, it's typically very small. So I can ignore that. And in order for me to actually I cannot do analytical solution in anything like this. I cannot do analytical solution in anything like this. This is actually relatively pretty. Now with flow around the spheres, I can actually do some upscaling. So upscaling is process of figuring out, hey, how do I get effective flux through something like this? Based on what I know on the microscopic end of the flow. And what we know is like those are the derivations flow through a tube, through an annulus, through a slit, and around a sphere. Those are the analytical solutions we have. So the question is, how do I get from flow through one such tube through essentially a networks of very irregular tubes? So the point I'm making is that it is very complex and something has to be thrown away. And throwing away some of the details is fine. I can't always deal with all the details. Question is, do I carry the gist of it up to a larger scale where I need to actually say something in an engineer? I need to engineer something. Okay? So that is an essential problem. It's often called upscaling. It can be done in numerous ways. It started as an experimental observation first, and we're going to go through that in general. So if you want to watch through it, so this is, by the way, a carbonate. Right? So carbonate and sphere packs are a little further away. so sphere pack is a good model for sandstone, or in general sedimentary rocks. Carbonates are sometimes sedimentary, but sometimes they're just evaporates, and they also have these like shells and little critters captured within that basically you can see part of it here. And this is a good old Texas carbonate, and you can see this is a core that was used in a 2008 thesis from this department. So essentially, the big question in this, so you can see the remnants of shells here, this little regular object. You can actually see evidence of this as you're walking around this campus. A lot of buildings are made from limestone blocks, so as you pass by them, you can see little shells. Right? So this is often a reservoir type of rock that we're dealing with. So this one is extremely buggy. So the problem here is the multi-scale problem. So not only that I have these larger bugs that are visible with my eye, so they're millimeter and up scale. Okay. But inside all of this, I also have microporosity. And that microporosity is my standard one, like in this rock, in between small grains of whatever evaporator was in there. Okay. So that's typically in between grains that are only around 1 micron to 200 microns, who knows? I gotta scan this rock to actually know. or do an SCA analysis metrology. So big question is, when I'm trying to simulate the flow through these type of things, is are these big things connected? If they are, then that's the dominant flow path. Okay? But if most of my oil is sitting in the matrix that is next to those big things, then whatever method I designed to flood this is just going to go through bugs and say bye to all the oil sitting in the matrix, right? And that's a problem. So I have to design methods that will plug these bugs, right? So that I force the rest of my, whatever my enhanced oil recovery method is, whatever flooding I choose to do, from low salinity to polymer to foam to you name it, okay? That it actually goes through this matrix and pushes the oil out that I need. So that's an essential problem in designing. And even in such designs, your question is, are these things connected? If they are, well, maybe I can go to transport phenomena and get some very simplistic formulas, analytical formulas, for flow through these tubes so that I can design my enhanced oil recovery method. And yes, I know that I'm not in control of all of the details, but maybe that's fine. If you're like me, you're going to go scan this rock and get all of the details and then simulate for 2-3 weeks to actually get that flow filled. But that requires having interest in pore scale modeling. And it's in itself, it can be a lengthy exercise. So if you need quick and dirty estimate of this flow that is maybe not the most accurate, you're still going to go through flux formulas that we developed in this class. Okay? So if you want to look at it again, you can. I'm going to put it in this. So our problem will be how to get the flow formulas in there. And just as a quick visualization, so basically if I pass by a rock and I take a core, I need X-ray vision to see inside. So these are my cross sections. They're not circular, and they're not even close, but I can still imagine sort of fitting a circle inside and figuring out where's most of my fluid going. So in this particular case, you see grains of a sandstone, and these are this is the empty space. This is actually from my PhD thesis. Images these days are way cleaner and way nicer than this one. This one has a lot of noise, which half of my thesis work was dealing with noise in the images and figuring out how to design methods that go past it. So this is really just about 1.25 millimeters on the side. So when I'm flowing through these, yes, I am in a slow flow mode, and I have my Stokes regime is fine. Okay, just doing Stokes equation is okay because it's controlled by such small grains that it has to be rather slow. Whereas if I'm in a wellbore, I'm flowing, and if I'm flowing through this tool, right, I'm flowing through an annulus that is a much larger length scale. So I have to think about that accordingly. And then this is also in the wellbore, so I have flow around it as well. Okay? So scale is something that you do have to think about. Now, if you think about single phase fluid, this is the Navier-Stokes equation that is in the pore spaces of this rock that I'm showing, and this is actually an example to the simulation. What you're seeing is just the magnitude of the velocity. And what I also see in there is development of a preferential flow path. This is something that is very specific for porous media. So even though I have tubes of all of the sizes and they're interconnected, there's the widest path where I have the least resistance to the flow, and that's where most of my flow is going through. And that's in that buggy example, those are the bugs. Okay? And that's why I'm bypassing the rest. So there's relatively stagnant zone here, so if I'm trying to flush something out of it, I'm in trouble. So what we are though interested is this large scale, so if I have in between two wells, I might have meters to kilometers, right? So essentially that's my reservoir scale, and this is where my operations are. So I might be, in this case, I'm injecting CO2 to essentially displace my bank of oil from injector to producer. And on that scale, we need an upscaled version, which is called Darcys Law. You can see that all of the non-linearities of Navier-Stokes in this process have disappeared. And we are using this simplified formula from the very beginning introduction that I am, hey, my flux is a linear function of the gradient. Okay? So I have a simple, and I have a coefficient here, two coefficients. Okay? One of them, this is Darcys Law, so this is permeability divided by mu. So one of them is capturing fluid, so that's fluid viscosity. We know a lot about it. And the other one is capturing the actual porous medium and its geometry. How complex is this geometry that I've been showing you? And how effectively can it transmit fluid through? Okay. So Darcy looked at it in 1856 for the first time. What he looked into is a flow in a sand column. Okay? And it's a relatively simple experiment. So the pressure was the simple pressure difference, simple to measure, okay, with your manometers. And here you can literally sit with a bucket and collect the fluid and see what the flux through is, volumetric flux. Okay. And based on the cross section, you can also see what the linear flux is when you divide it by that area. And what he realized is when he plotted the results of this flux Q, then versus whatever was the pressure head, essentially you see, so a simple linear relationship. And that was the motivation to essentially formulate this Darcys Law. Now, it's a simple fitting exercise, a curve fitting exercise to a very simple curve, linear. But nevertheless, it reveals some essence that we capture with this type of model. We're capturing the essence of flow through this porous medium. And it's an experimental observation. However, it does have a theoretical basis. So that blue sphere pack, if I actually take that blue sphere pack, there is a mathematical method. And if you make it periodic, so it repeats itself on all sides, you can design a sphere packing that kind of, whatever sphere is cut on one side, it continues on the other side. So if it's periodic in all directions, and all of the spheres are of the same size, you can actually get in the formal mathematical exercise, you can scale up from Navier-Stokes or rather Stokes equation up and get the Darcys Law. So that was done separately. If the Whittaker in 1984 has a paper in Transparent Force Media, if you're ever interested how that looks like. So essentially, but that is an independent theoretical assessment of this experimental result. As I've been pointing out at the beginning, results that have such both theoretical foundation, which might typically come later and after the observation is made, and the actual observation in the nature are the strongest ones. That's where we actually understand what's happening. Now, what you actually kind of throw away in the details of the flow field through that sphere pack, you throw away the inertial effects in these small crevices, and you kind of take just the bulk through the middle of these pore spaces, and that gives you effectively Darcys Law. And so that's what we're throwing away, and we're going to go through a similar exercise to get the permeability value. So my Darcys Law, again, it's a linear law. It's quite intuitive. If I don't have pressure gradient, I don't have flow. And I will always flow from high pressure towards low pressure. Hence, we have that minus in there because I'm flowing against my coordinate system. Right? And in general, this flow could be different in X, Y, and Z. That's pretty obvious here. Right? I have this medium. These fractures connect in this, that I can connect from here to down, but I don't connect this one necessarily. Okay? So, or I might, but in a very different way. Was there? There's no bell, was there? I was like, I don't hear well, but I don't hear that badly. Okay. Okay. So basically, in general, I actually have permeabilities that are different in different directions. And I know you love tensors by now. Permeability is actually a tensor. It's just in most cases we have tensor multiplying gradient of pressure, which is a vector, right? And the result is a vector. And that's my flux vector. And its XYZ components might be different. In here, they are. Okay? But if you don't have something like this, if you have something that looks kind of the same, however you turn it around, which we refer to as isotropic, then you're going to ignore all of that, and you're just going to calculate one number, permeability, that is the same way, however you turn it, which is equivalently, basically, this tensor just having k, k, k on diagonal and 0 otherwise. Okay. So that's what we're going to assume, and we're going to next time divide Karman-Kozeny.